Welcome! Today we are going to make the invisible visible. We're diving into electric fields, these unseen forces that, let's be honest, power our entire world. And we're going to learn how to draw them using some simple, elegant, and completely imaginary lines.
So this really gets to the heart of the problem, right? Electric forces are everywhere, but we can't see them with our eyes. So how in the world do you work with them? How do you possibly map out a force that's totally invisible?
Well, the answer is this brilliant idea called electric field lines, and you can just think of them as a set of instructions. They're imaginary curves for sure, but they show us something incredibly real: the exact direction an electric force is pushing or pulling at any single point in space.
Honestly, the best analogy is a weather map showing wind patterns. You know those lines that show you which way the wind is blowing? Well, electric field lines do the exact same thing, just for the electric force. It's a perfect visual guide for a phenomenon we can't see.
Okay, so if we want to draw these force maps accurately, we have to follow a few simple but very important rules. Think of them as the fundamental laws of the game. Once you know these, you can map out basically any electric field you can think of. First up, rule number 1. These lines are not just random squiggles on a page. Nope, every single line has a very specific place it starts and a very specific place it ends. They're like predictable one-way streets.
And here it is, the most fundamental rule of all. Electric field lines always start on a positive charge and they always end on a negative charge. It's a one-way trip from positive to negative. There are absolutely no exceptions.
And here's a really cool way to picture it. Imagine you could place a tiny, free-floating positive charge inside an electric field and just let it go. The path it would naturally follow, the journey it would take, that is the electric field line. All right, on to the next rule. And this one is a big one. It's the one that can never, ever be broken. Electric field lines can get really close to each other. They can bend and curve all over the place, but they will never, ever cross.
But why? Why is this such a rigid, non-negotiable rule? Just take a second and think about it. What would an intersection, a crossing of lines, actually mean for the force at that one single point?
And here's the beautifully simple reason. If two lines were to cross, that would mean that at that one single point in space, the electric force is trying to point in two different directions at the exact same time. A single force just can't do that. It's physically impossible. Simple, right? But so profound.
But these maps tell us more than just direction. They also give away the strength of the force. And the secret to seeing that is all in the spacing of the lines, how crowded they are.
It's a really simple rule of thumb. Wherever you see the lines are all bunched up, practically shoulder to shoulder, that's where the electric force is powerful and intense. And where they spread out, with a lot more space between them, the force is much weaker. So a quick glance at the map tells you exactly where the action is.
Okay, so we know the rules of the game. Now let's stop talking theory and actually put them into practice. Let's see what these maps really look like for some common setups.
So let's start with the absolute basics. For a single positive charge, the field lines just radiate straight out in all directions, like rays from the sun shooting off forever. For a single negative charge, it's the total opposite. All the lines point inward, like space itself is just converging on that one point.
Now, let's bring a positive and a negative charge near each other. This is where the magic really happens. So first, the lines erupt from the positive charge, just like before. But now, they have a destination. They start reaching out, seeking the negative charge, and they begin to curve through space. And as they do, they push against each other, they bend, but remember, they never cross. And the final result is this beautiful, elegant, arcing pattern. This is the classic dipole field.
So what happens if you put two positive charges together? Well, the lines still erupt outwards from both of them, but since they can't cross, they're forced to bend away from each other. They literally repel each other, creating this empty zone, this void, right in the middle where the field is weakest.
So you see, once you know the language, you've cracked the code. We can now look at any of these maps and know exactly what's going on. Let's do a quick recap of what this powerful visual map tells us at a glance.
All right, let's run through the code one last time. The lines show direction. That's the path of the force. They always have a clear start and end, from positive to negative. The absolute cardinal rule, they never ever cross. Their density tells you the strength. Closer together means a stronger force. And one last key detail, these electric lines never form closed loops, unlike magnetic field lines.
So here's the main takeaway, the crucial point. We're using a completely imaginary concept to visualize, predict, and engineer very, very real forces. I mean, from designing the antennas that give us Wi-Fi to guiding particles in giant accelerators, drawing this simple map is always the first essential step.
So I'll leave you with this thought. We started this journey trying to map an invisible force, and we did it using imaginary lines. But the patterns they revealed, these elegant geometric rules, are completely real. So even though the lines are a fiction we created, they describe a fundamental truth about our universe. What does that tell us about the hidden fabric of reality itself?